Hello everyone, welcome again to Modeling Methods in Mechanical Engineering, and today we're going to discuss more axisymmetric problems, more problems of in cylindrical coordinates by the use of the separation of variables and superposition methods, but in particular we're going to concentrate on axisymmetric problems, those problems in which the solution does not depend on the angle theta on a cylindrical coordinate system. So it might be problems that depend only on R or R and Z or just only on Z. Now, obviously for a problem not to result, or for the solution of a problem not to result as a function of theta, neither the initial condition nor the boundary conditions have to be functions or could be functions of theta. That would actually be the requirement for the solution not to be in this case. So this is modeling methods in ME, and we are looking now at separation of variables in axisymmetric problems, essentially where the temperature or whatever field variable we're solving for is not a function of theta. So let's start with a problem where the solution or the problem is it is known that it's a function of R and Z. And assuming that, again, we're working on a steady problem, so we're going to let, by separation of variables, T of R and Z be R of R and Z of Z. And this is assuming the separation of variables applies. Essentially, you only have one non-homogeneous boundary condition. So the governing equation for this problem, remember we're dealing with the Laplace equation, is equal to 0, which in R and Z reduces to simply 1 over R d dr R dt dr plus the second derivative of t with respect to z squared equals 0. So this is a Laplace equation in cylindrical coordinates, and we've eliminated the theta dependency, so it's axisymmetric. By implementing this assumption into the governing equation, we end up with R of R, R double prime of R, over R of R plus 1 over R, R prime of R is divided by R of R. This is after separation. We sent all the R's to one side and all the Z's to the other side. Z double prime of Z divided by Z of Z. And that is equal to, since the left-hand side and the right-hand side, the left-hand side is a function of R, the right-hand side is a function of Z. We've done this before. We can conclude that this can only be possible if they're both equal to a constant. And then we're going to force the sign of that constant depending on the direction of homogeneity. Right? So basically, case 1 would be if the Z direction is homogeneous, then we select plus lambda squared. In case 2, if the R direction is homogeneous, then we select minus lambda squared. Right? So basically remember that this is the Z axis. We're going to draw the y-axis in this direction and the x-axis in this direction, and then we're going to superimpose a cylinder here. And remember that R and theta are defined this way. Well, Z actually remains the same. Z-axis is the Cartesian coordinate system. So these two cases imply basically that case number 1, the Z direction is homogeneous. So the boundary condition on the bottom of the cylinder and on the top of the cylinder are both homogeneous. And they can be first, second, or third kind. Case number 2 implies that in the R direction, the condition is homogeneous. Whether this is a solid cylinder, then the boundary condition on the periphery, first, second, or third kind, will be homogeneous. And if this were a hollow cylinder with a hole in the middle, then the boundary condition inside and the boundary condition on the outer periphery will be homogeneous in both of these cases. So case number 2. All right, and in no particular case in here, the solution will be a function of theta. Neither the boundary conditions nor as you can see, the equation itself is not a function of theta, so there cannot be any theta dependency. So let's start with case 1. Case 1, the z direction is homogeneous, meaning that the boundary conditions in the z direction is homogeneous. So we pick the plus sign on the separation constant, and the equation in z will result c double prime of z plus lambda squared c of z is equal to 0, plus 2 homogeneous boundary conditions. And if that's the case, well, this is the equation we end up with. We know that the solution, z of z, is a cosine of lambda and z plus b sine of lambda and z. And we know that the lambda n's eigenvalues, the ZZ eigenfunctions, function, and the n of lambda n norm, and all these could be found from Cartesian table. Same table we use to solve for Cartesian problems. We have 9 possible combinations of boundary condition types, both homogeneous on both sides. Then we can deduct which one of either the cosine, the sine, or combination of the two survive. What is the eigenvalue? What are the eigenvalues? And what is the norm? Basically, the integral of the square of the eigenfunction over the domain. So, in the R direction, so let's we end up with the equation in the Z direction if we pick the plus sign for the separation constant, and then in the R direction we end up with the following equation. In the R direction, for case number 1, we end up with R squared, R double prime of R, plus R prime of R, minus lambda n squared, R of R is equal to 0. And as you can see, this is not the Cauchy-Euler equation because we have the square term, the linear term, and again another square term. This is some sort of a Bessel equation, but the minus sign indicates that this is the modified Bessel equation, whose solution is not oscillative. So this is the modified Bessel equation of order 0. Okay, for which we have R of R is some constant of integration C, the modified Bessel function of the first kind of order 0, plus D times the modified Bessel function of the second kind of order 0. That is a solution in the R direction. Now, if the solution, remember, looks like this. This is R. This is the functions, and the solution I0 goes like this. This is 1, and the solution K0 is singular at R equals 0. So it goes to infinity at R equals 0, and it decays asymptotically as R equals infinity. So if the cylinder is solid, if we have a solid cylinder, basically means that the solution T of R and Z, and therefore R of R must be finite at r equals 0. And if the solution has to be finite at r equals 0, then we can essentially conclude that d should be equal to 0. So only the Bessel function, or the modified Bessel function of the first kind, will survive if the cylinder is solid. If the cylinder is hollow, then we would have to apply the boundary whatever homogeneous boundary condition there is, either inside or outside, to see if either the I0 remains or the K0 remains. Now, case 2, remember, the R direction is homogeneous. If the R direction is homogeneous, we pick the minus sign of the separation constant. And if we pick the minus sign of the separation constant, the equation that results is this. Now, this one is a regular Bessel function, Bessel equation with a plus sign. So, but it's the order 0 equation. So this is the Bessel equation. Bessel equation of order 0. And that equation has solutions A times the Bessel function of the first kind of order 0, lambda nr, plus B, Bessel function of the second kind of order 0, where, remember, these functions are now oscillative. Plotted these functions. Remember, J0 goes like this. This is 1. So this will be J0. Well, Y0 would be singular at r equals 0. It's minus infinity to be precise. This is Y0. So, again, we can go to the same exact argument that if the cylinder is solid, if solid cylinder, then the temperature, and therefore R of R, must be finite at R equals 0, and therefore B should be equal to 0. So we cannot keep Y0 in the solution, because otherwise the solution would be infinite at R equals 0. Now, I've posted a table provided eigenvalues, or starting with eigenfunctions, and eigenvalues, or actually comma eigenvalues, and norms tables for cylindrical problems. Cylindrical. So there's two types of tables, one for solid cylinders and one for hollow cylinders. And this will dictate the eigenfunction, the eigenvalues, and the norms. Okay, depending on the boundary conditions. So this is all depending on the type of homogeneous species. 1, 2, or 3, or second or third kind. So You can find these tables online. I've posted them on Canvas. And for example, for the solid cylinder case, this is the equation. And notice that the entire equation is divided by r squared, which is okay. And this is also an equation that shows a beta square, and it shows a nu square divided by r squared, so that it's an equation that it allows to have an order. The equation that we're solving in this case is order 0, so for this case, nu is equal to 0, so all that remains is the eigenvalue beta square in the equation. And depending, in the case of the solid cylinder, whether the boundary condition outside of the cylinder on the outside periphery is third kind, second kind, or first kind, then the eigenfunction will be always the j, the first kind, the Bessel function of the first kind. The inverse of the norm is this, and the eigenvalues are those that actually satisfy these implicit equations. So basically, the roots of the roots of the Bessel function of the first kind of order nu, in all these cases. And there's eigenfunctions and eigenvalues for the hollow cylinder case, the same exact equation, but now we have two boundary conditions, one in the inner periphery and one in the outer periphery. So we have 9 possible combinations of boundary conditions. Actually, this table has 2 pages, so to reach all the 9 possible combinations. First kind, third kind, second kind. This is inside and outside. Boundary condition of r equals 0, boundary condition of r equal b. Same distribution, so we have the norm, the eigenfunctions, and the roots of the equation. The eigenvalues dictated by the roots of these particular equations. So it's all here. We don't have to solve those equations, and we don't have to implement the boundary conditions. They're all solved for our perusal. Now that's the solution in the r direction. We'll solve an example to show how it goes, but in the z direction, the equation that we end up with is z double prime of z minus lambda n squared of z times z of z is equal to 0, which has a solution. Again, this is not an eigenvalue problem because of the minus sign. C cosine hyperbolic of lambda n z plus d sine hyperbolic of lambda n z. Where the lambda n has already been determined from the r problem using the tables. So what we do, as always, is apply remaining non-homogeneous boundary condition to assemble or to assembled solution, and determine the constant of integration using orthogonality. All right, so let's go straight into an example to show how this works. Again, we're dealing with axisymmetric problems. So, example, we have a governing equation is the Laplace of the temperature in R and Z equals 0 with boundary conditions. The temperature B, C, so on the outside periphery, is equal to 0. The temperature R, 0 is equal to 0, and the temperature R, L is equal to some function f of r, and that's given. So basically, let's draw the cylinder. So on the top, we have the temperature equals to some f of r, some temperature on the some given value of temperature. That is a function of r. It's different in the center than towards the outside. The temperature is equal to 0 on the bottom plate, so this is the z direction, and on the outside periphery, the temperature is equal to 0. So all first kind conditions. And as you can see, in the R direction is homogeneous, and in the Z direction is non-homogeneous. So that will help us pick our separation constant. Again, the equation is 1 over R ddr R dt dr plus the second derivative of t with respect to z squared is equal to 0. And we're going to let t of R and z be equal to R of R, z of z. As we've done already, the resulting equation will be R double prime of R over R of R plus 1 over R, R prime of R over R of R is equal to minus C double prime of Z over Z of Z. And we are going to pick a negative separation constant so that we end up with an eigenvalue problem in the R direction, right? Because the R direction is homogeneous. So the R problem is going to be R squared R double prime of R plus R prime of R plus lambda squared R of R equals 0, subject to R at radius equals 0 should be finite. We don't have a condition there, we just know that the solution has to be finite, and at B is equal to 0. So those are the homogeneous boundary conditions. So that's the equation that we end up with and the conditions that we end up with, separated already because they're homogeneous. So the solution to this equation is A J0 of lambda R plus B Y0 of lambda R. Again, since R at radius 0 should be finite, that results immediately into B equals 0. So we cannot keep the Bessel function of the second kind because that one's singular, R equals 0. So if R of B at radius equal B is equal to 0, then 0 should be equal to A J0 of lambda B. So we go to the same argument as we've done so many times. There's a product of A times J0 should be equal to 0. A cannot be 0 because that will render the entire solution trivial. R will be 0 and then therefore T will be 0. The only option is for J0 to be 0. So J0 of lambda B should be equal to 0. And since J0 is a function that oscillates and crosses the axis an infinite number of times, we can conclude that then therefore lambda n should be the roots of the Bessel function of the first kind of order 0 is the nth root divided by b. So these are the eigenvalues. And essentially Rn of R equals just simply the remaining function, which is J0 of lambda n of R. These are the eigenfunctions. All right. So in the Z direction, we have C double prime of Z minus lambda n squared C of Z is equal to 0, subject to only one separable boundary condition that says that at the bottom plate the temperature is equal to 0 and therefore Z of 0 has to be 0. The top boundary condition we cannot separate because it's not homogeneous, and therefore Z of Z, which results in the C times the cosine hyperbolic of lambda n Z plus D times the sine hyperbolic of lambda n Z, and such that Z of 0 must be 0, which is equal to the cosine to C times the cosine hyperbolic of 0 plus D times the sine hyperbolic of 0. The sine hyperbolic of 0 is 0, and the cosine hyperbolic of 0 is 1, and therefore we can conclude from here that C should be equal to 0. And C equals 0 means simply that Z of Z is just D times the sine hyperbolic of lambda NZ. So we end up with a single function, a single constant of integration, and then we can just simply combine the temperature of R and Z should be equal to, well, R of R times Z of Z, which is equal to the summation from n equal 1 to infinity, dn times J0 of lambda nr sine hyperbolic of lambda nz. And that is the general solution to this problem. As after we assemble them all at all possible eigenvalues, at all possible frequencies of the Bessel function. This is a general solution. So what we do next is apply remaining non-homogeneous condition, the one that says that T, R, and L on the top of the cylinder, we have a boundary condition that says FR. So basically, we plug this into the left-hand side. FR should be equal to the summation from n equal 1 to infinity of the n J0 of lambda nr times the sine hyperbolic of lambda nl. At T equal L, this is what we have for boundary condition. Remember that Bessel functions, in particular this one, which is the eigenfunction for this problem, is orthogonal with respect to a weight function R. Remember, that comes from the definition of the classification of Sturm-Liouville problems, that if you look at the governing equation, the weight function is embedded into it. So as, for example, the sines and cosines are orthogonal with respect to each other, with respect to a weight function equal 1, the Bessel functions need a weight function of R to be orthogonal. So that means that we have to multiply both sides not only by the eigenfunction at a different frequency, but also times R, so that when we integrate on the right hand side, we take advantage of orthogonality. So on the right hand side, we'll have dn J0 lambda nr sine hyperbolic of lambda nl. Then we have J0 of lambda mr and an r. Multiply both sides by J0 lambda mr and r. Then we integrate from 0 to b, which is the domain in the r direction. J0 lambda mr of r dr is equal to, and then we integrate the right hand side, but that passes right through this summation. And I'm going to move the sine hyperbolic over to the front of the integral. This is not affected by an integral from 0 to b in the r direction. So this will be J0 of lambda nr, J0 of lambda mr, r dr. And this right here is the norm, only when n is equal to m. So this is equal to, so this is 0 if n is different than m, and it's equal to the norm of lambda n if n is equal to m. That's what we've usually done. So again, the norm now requires that r to be in there. So basically, what we have is the integral from 0 to b, f given boundary condition, and J0 of lambda mr, r dr is equal to dm sine hyperbolic of lambda ml times the norm of lambda m, which can be found directly on the table. And then I can switch notations back from m to n, switch notations from m to n, and what we end up with simply is that the constant of integration dn is 1 over the sine hyperbolic of lambda nl times the norm of lambda n. That's why when we look up on the table, the norm appears as 1 over n, because it's usually used that way. 0 to b, j0 of lambda nr, r dr. And there we go. Now we have the particular solution. All constants of integration are given by this. Right? So obviously, depending on what that boundary condition is, it's a function of r. If it's a constant, it's just basically the solution of the integral of j0 times r. So for this particular case, where boundary conditions in the r direction is first kind, rb equals 0, the norm, which is the integral from 0 to b of r j0 square of lambda nr dr is equal to b squared times j0 prime of lambda nb square. That comes directly out of the table. So if we go to the table here for solid cylinders, for the case number 3, when the boundary condition is the first kind, the norm, or this is the inverse of the norm, I think we're missing a 2, j prime, yeah, we're missing a 2 in here. So it's b squared over 2. Fix this here. Yes, b squared over 2. So this would be b squared over 2 from table. Solid cylinders. So the axisymmetric solution can actually be plotted in a rectangular frame, because remember, theta doesn't come into play. There's no theta dependency anywhere in here or in the general solution. So R and Z. So we can basically, our axisymmetric solutions are plotted in an R Z coordinate system, where Z is the axis of rotation, and this goes from 0 to L, and this goes from 0 to B, and basically what you have is a rectangle. A rectangle like that if it's a solid cylinder, or a rectangle that starts at a value that's different than 0 if it's a hollow cylinder. And then here we have t equals 0. We have a finite solution at r equals 0. We have a solution t, or a boundary condition t equals 0 here. And then we have a t that's some function of r. And then the solution will propagate in this rectangle given by this equation, or this general solution that we consider, or that we derived. Now, that's as far as it goes for axisymmetric cases, steady state axisymmetric cases. We looked at solutions in R and theta, this polar coordinates. We looked at solutions in R and Z, axisymmetric. So what if all dependencies remain? The problem is neither polar nor axisymmetric. So we consider 3D steady cylindrical problems. That means that the temperature should be a function of r, theta, and z. temperature or any field variable. Remember that's our premise here, that we're illustrating this whole concept using heat transfer, but it doesn't have to be. Okay, so we'll have a few possible cases depending on where the homogeneous conditions are. So case 1, theta and z are homogeneous, and R is non-homogeneous. Again, as always, we'll let T of R, theta, and Z be equal to R of R, theta of theta, Z of Z, and R double prime of R. This is what the resulting governing equation would be. Remember, we're solving the Laplace equation, but now it's in 3D. Cylindrical. This is R of R plus 1 over R squared, theta double prime of theta, theta of theta is equal to minus Z double prime of Z divided by Z of Z. And we pick a separation constant that's positive because we want to form an eigenvalue problem in the Z direction. And later we'll pick another separation constant to build an eigenvalue problem in the theta direction. Remember that in the theta direction, or homogeneous basically means that it's periodic, that we have a full circle. So we've done this already in the polar coordinate problems. In the C direction, you have C double prime of C plus lambda square of C equals 0, plus some homogeneous boundary conditions, first, second, or third kind, on the top and on the bottom. And then we'll basically have Z n of Z will be sine or cosine eigenfunctions. Lambda n are the eigenvalues, and n of lambda n the norm. And thus from Cartesian table. Okay. Same one we use for x and y. Then what we have left is R squared, R double prime of R divided by R of R. So we're multiplying everything by R squared so that we can get rid of these R squared in the denominator of theta. R squared divided by R, R prime of R of R, minus lambda n square R squared is equal to minus theta double prime of theta divided by theta of theta. And then we apply another separation constant. We call it nu, and we're going to make it square, obviously, to fix the sign. And we're going to make it positive so that we build an eigenvalue problem in the theta direction. So in the theta direction, we have theta double prime of theta plus nu square theta of theta is equal to 0 plus periodicity or homogeneous boundary conditions if wedge. So theta 1 and theta 2. So we have a wedge instead of a full circle, then we need homogeneous boundary conditions at the first end of the wedge and the second end of the wedge. I'll illustrate that in a second, towards the end. So theta of theta is simply C times the cosine of nu m theta plus d times the sine of nu m theta. Where, because if we have a full circle, then nu m is basically integer numbers. It's the only way to maintain periodicity. If full circle from periodic conditions. We'll address what happens when you have a wedge in a moment. But let's first go into the R direction. In the R direction, the resulting equation is R squared R double prime of R plus R prime of R minus lambda n square r square plus nu m square r of r is equal to 0. Now notice because of that negative sign, this is a Bessel function of order nu, but is a modified one because of the minus sign. So this is the modified Bessel equation of order nu m, whose solution r of r is equal to some constant of integration e times the modified Bessel function of the first kind of order nu m of lambda n r plus f times the modified Bessel function of the second kind of order nu m lambda n r. And now we have enough to construct the general solution. So assemble solution TR theta z equals R of R theta theta C of z, and apply remaining non-homogeneous boundary condition at R equal A, or sorry, not R equal A, or at R equal A or R equal B. If it's a solid cylinder, it's just R equal B. If it's a hollow cylinder, the boundary non-homogeneous condition could be at R equal A or R equal B. So at the end of the day, the general solution would be a double summation from n equal 1 to infinity, m equal 1 to infinity, constant of integration C and m to whatever R of R is, whichever of the two remains. So if it's a solid cylinder, remember f has to be 0 because the modified Bessel function of the second kind is infinity. So for a finite solution, this will go away. If it is a hollow cylinder, then one of the two will remain, or a combination of the two, depending on where the homogeneous boundary condition is. You have to have at least one homogeneous boundary condition. Remember, if these doesn't apply, then if you have more than one non-homogeneous boundary condition, then you have to resort to superposition to build multiple problems, as we did in Cartesian coordinates, with only one non-homogeneous condition. All right. So that is in the case where, that's case number 1, where the non-homogeneous direction is R. Then, case 2, what happens if Z is the non-homogeneous direction and R and theta are homogeneous? Whether it's a a solid or hollow cylinder, and theta, whether it's a circle, full circle, or a wedge of a circle. In this case, the process will dictate that theta of theta go to the same separations. It's just that the sign of the separation constants will be slightly different. Plus b sine of lambda n theta. R m of R will be now the Bessel functions of the first kind, not the modified Bessel functions of the first kind of order nu m, lambda nr, plus d times y nu n of lambda mr, and the function in the z direction would be the cosine hyperbolics and sine hyperbolics, lambda mz plus f times sine hyperbolic of lambda mz. So these are the functions, the result of the separation. Again, such that lambda n should be equal to n, should be 1, 0, 1, all the way to infinity, if full circle. So periodicity that dictates that, but if we don't have a full circle, nu m is not an integer, and that is if section circle. Theta 1 to theta 2. Again, we'll illustrate that in a minute. And lambda m's are from homogeneous boundary conditions in the R direction. Whether first kind, second kind, or third kind, you go to the table and get what the eigenvalues are and the norm itself. And finally, what happens on case 3? Case number 3 of steady problems, and in this case, theta is in non-homogeneous direction, and R and Z are homogeneous. And whether it's a solid or a hollow cylinder, both or a single condition in R are homogeneous, and in the top and on the bottom at Z equals 0 and Z equals L, they're homogeneous. And now in order for the problem to be non-homogeneous in the theta direction, it cannot be a full circle, it would have to be a wedge. So to illustrate this, let's see if this is the Z-axis. Let's say that this is the R-axis, and then this is also the R-axis. I think I drew that angle a little bit too steep. That's okay. So this is the R-axis. And this is the R-axis as well. So let's see if we have a wedge of a cylinder. A wedge of a hollow cylinder would look like this. There you go. So this is a wedge of a hollow cylinder, and this is the angle theta. This is the tangential coordinate. This will be theta 1. This will be theta 2. All right. So in this case, there is no eigenfunction expansion. It is possible for this problem. Well, it's not that it isn't possible, it just hasn't been found. We can use superposition to construct problems where the theta direction is homogeneous and transfer the non-homogeneous conditions to R and Z directions. So that can be done. So depending on what non-homogeneous boundary condition you have, either here or on the other side of the wedge or both, then you can break it up into two problems, and then in each of those two problems you alter the dependent variable t so that you transfer the non-homogeneity over to the R direction or the Z direction. So you always end up with a homogeneous problem in the theta direction. Otherwise, there's no eigenfunction expansion that has been able to work out for these particular problems. So this is it. This is what I wanted to cover today in terms of eigenfunction expansions and separation of variables for steady problems in cylindrical coordinate system. In the previous class, we had already looked at polar coordinates, or basically the problems that depend only on R and theta. And now we looked at axisymmetric problems that depend on R and Z, and also the possibility that the problem is three-dimensional, neither axisymmetric nor polar, but still steady, no time dependency. So thank you for your attention, and I'll see you next class.